when I like do something.
Okay, let's start. So this week we're gonna look at dynamic programming. So just before I start with anything, so the first problem set of homework is still in the week, and also everything is just from the previous lecture. Like nothing about dynamic programming is in the homework, right? And also for anyone who signed up to scribe things from last week, so like the deadline is approaching. So okay. All right. Just to start with dynamic programming, the first problem that we can look at is a very natural problem of trying to like schedule a bunch of jobs into one machine. So let me explain the problem. So the problem is that you are given a set of jobs, J1 to Jn, right? And for each job, like each job Ji, you have basically three numbers. The first number, Si, just say the starting time of this job. And the second number is the finish time. So basically, each job looks like an interval in the line, in the real line. And now each job will have value V. Okay. And what we're gonna say is that the set of jobs is compatible if they don't overlap. Like this set of jobs, for example, they don't overlap with each other, then that's good. If I instead put this job, let's say this one, into my set, then it's not compatible because it overlaps with this guy. Okay. And now the very natural question is that what we want is just a compatible subset of jobs that maximize the total value. Right? You have one machine, you want to pack a bunch of jobs as much as you can that maximize the value. Okay. The problem makes sense? Okay. So now let's see. So how do we want to solve this problem? Well, let's try to think like similarly like before, actually. So the way to think of how to come up with dynamic programming algorithm and divide and conquer algorithm are similar in the sense that what you want to do is just to try to solve the same problem but with smaller size. So we want to do recursively. Okay? And now let's try. Okay. Let me try to first. Let's set up this set of jobs now. They are ordered by the finish time. Okay. And now if we just consider the last job, this guy, the last one. Okay. What do we have? We have basically just two options about this last job. We want to add it into our collection or reject it. Okay. So suppose that we just reject it, right? Then now you see that the remaining what remains is just the same problem, but we have now one less number of jobs. So what we can do is just to recurse. And let me close this door. Oh, sorry. Last person. Sorry. So now, well, there is another, like we have two choices, right? Whether we want to reject or accept it. If we know that we should reject it, then the maximum value that we need to compute here is just to look at the same problem but one less job. But now if we say that we're gonna accept it, then what do we know? We can just say that the value that we're gonna get from this collection of jobs is that at least we add the last job into our collection, so we have value Vn. And now, like how should we recurse? So it's very natural to just look at the last job. Like let's say that I is the last job that doesn't overlap with Jn here. Okay. So which one is the last job that doesn't overlap with Jn? So this guy. So and this guy is overlapping with Jn. So what we should do is just look at the last job that doesn't overlap with Jn, so this guy, and just recurse on everything from here. Okay. Okay. So basically, we just need to reject these two guys. And yeah, and that's I is just n-3 in this case. Okay. So this is the algorithm. Does it make sense? Like it's just you sort it like here, like you have like a list of interval. There is a natural way to sort them. Just sort that, and now like you just consider the last job, and you have two choices what to do. For each of the choice, it gives you some kind of recursive equation. Okay. Good. So now, so if you look at this, it's kind of similar to what we looked last time, right? The maximum independent set problem. We have a graph. We look at a node. Each node have two choices whether to add into your collection or not. This is kind of the same, but you will see soon that like there is something very special about this problem that makes it much faster. Like we can solve this thing much faster. But anyway, so now, just from the last like the previous discussion, we can see that this just gives you a very natural algorithm, right? You have the job, like all these jobs sorted by the finish time, and then you just write down the recursive algorithm. So let I be the last job doesn't overlap with Jn, and just what you should return is just the maximum between two choice. This is just the best solution when you reject the last job, and this is the best solution when you accept the last job. But if you look at it like this, like how does if you just write down the recursive, so this is correct. But now let's analyze the running time, right? So it looks like the recursion will look something like this, right? For each job, like the last job here, we just spend constant time per round. But when we recurse, we might recurse into sub-problem. Each of a problem have size like maybe at most n-1. And so the recursive running time looks something like this. And we have seen this before. And that is something like 2 to the n, because you branch out, like you branch, you have like a factor of 2 of branching factor, and like the depth is n. So that's the 2 to the n, if you just analyze it like that. So now that's kind of disappointing, like why like something actually seems off. And there is actually one key observation that once you see it, you will see that, okay, we should be able to save a lot of time. I would like to ask you, do you see some some observation that this analysis seems like a very redundant? Why is that?
I think a lot of the subproblems get solved over and over again.
Yeah, exactly. Can you say a bit more why the many subproblems are actually looks like the same subproblem?
Yeah, sure. Let's say you select let's say you reject a job and then you have to focus on 1 to n-1 jobs. And let's say you select it, so J1 up to I. So that subproblem right there gets solved twice.
Yeah, good. So very good. So let me just let's make that formalize. So you see, when you have this problem, right, and we do recursion, let's look at the form of subproblem that we ever look at. It only looks like this. It's always the same order of job, sorted, but up to the job I, when I is something less at most n. Which means that the number of distinct subproblem that we ever look at, there are just n many subproblem possible that we ever look at, right? But here there are 2 to the n nodes in this tree. It means what? There are 2 to the n node, but there are actually n distinct subproblems. So actually many of these subtree actually looks like it just looks like the same subtree if we recurse. So it means that if we just expand the subtree like this, we actually redo a bunch of recomputation. We redo the same computation again and again. So now, how should we avoid that? Yeah.
Sacrifice some space, just store the result from a subproblem.
Yeah. So good. To avoid this recomputation, just remember what you have computed. Right? There are just n many ways to n many things that you're gonna look at anyway. If you have, let's say, if you have computed this subproblem from J1 up to Ji, you know that you're gonna look at this answer soon enough. So you just remember that, and whenever you need to look at it again, you don't need to recompute. So now let's write down the recursive algorithm such that you remember what you have computed. So let's say that now you have the array, call it memo. It's just a lookup table where this is a global array that you have, and memo k is what is just store the solution when you recurse from J1 up to Jk. Okay. And now you can write down the same algorithm. You have this kind of recursion, right? And but the point is that now, if you want to solve this problem from Ji up to Jn, what you do first is that you check if you have remembered this, if you have computed this before, and if actually you have computed already, just return it. Otherwise, you didn't compute it before, so you just now just recurse just like before. And once you finish your computation, now you remember. Okay. So does it at least make sense, this algorithm? Okay, good. So we're gonna see how to analyze this soon enough. But for now, like when I write it like this, it's like I say this is top-down dynamic algorithm, dynamic programming, because you still just do recursion, except that whenever you have computed something, you remember what you have computed, and it's top-down because you recurse. We will see soon, like you can do it bottom-up too, and that has some advantage. Anyway, this top-down dynamic programming is now look like this, right? It's kind of like divide and conquer. You have some tree that you branch, but you try basically to reuse the tree node that you have recompute. So hence this picture. Anyway, let's try to write down like another way to write down the same algorithm, but bottom up. Okay. So what you're gonna do is that the same thing. You have this memo to be array index from 0 to n, and memo I should store the recursion for like a j1 up to ji. Right? And what we're gonna do is just try to fill up this table from small number to large number. Yeah. And that is gonna look like this. So, like, just consider for each k, right? For each k, you have two choices, whether you wanna reject or accept jk. If you reject, you just use this thing, right? Just like everything up to jk minus 1. If you accept, you get this number vk plus memo I, where I is just the last job that doesn't overlap with jk. Okay. And you see that this will work because like you iterate from 1 to n. In the iteration k, you will only look at memo from the previous from the previous index that you have already computed. Okay. So now there is an easy way to analyze this this algorithm. Like you can compute I in the easy way that you just scan through the jobs. That takes n time, and there are n many iterations. So the running time here is going to be n squared instead of exponential. Okay. So now, like you see, like there are like this problem. You can solve it with dynamic programming. There are two ways to do it. You can do it bottom up. So this is sometimes slower in practice because what you do is that you just fill up all the memo from the beginning. You fill up all the memo that you ever need. You can write it in the top-down way as well. Sometimes it's faster because you might just or only compute the like you just fill in something to the table memo only when you really need it. So you don't need to compute all subproblem. Okay. But you see, like when you have top-down, when you write the top-down approach, it's much clearer how to analyze it. And you know that, but like for the the bottom-up one is much clearer to how to analyze it because it's just a for loop like this, right? And the top-down one is like you know that it can be only faster, but it's not clear to how to analyze it. Like if you just don't write a bottom-up one. Yep.
Can you use the runtime of the bottom-up to prove the runtime of the top-down, or is that not applicable?
Yeah. So you can say that like this needs some argument, but the point is that whenever you like, so okay. How to say this in a formal way? Like you never spend more time for top down more than bottom up one, but this needs some argument. I don't see how should I explain that clearly right now.
No worries.
Yeah. Okay. Anyway, if we care about worst case analysis, they're kind of the same, and you can just write the bottom up approach because it's easier to analyze. Okay. So you have seen the algorithm that takes n square time, and you see like I just said that in each round here you can spend n operation to find the index I that doesn't overlap with JK. Actually, you can optimize this to just log n. So any ideas how should you do that?
Yeah, binary search, because the end times are sorted, so you can binary search with the start time of the thing you just chose.
Exactly. So all the jobs are sorted by the finish time. So you like now you just want us to know like the last guy that doesn't overlap with JK. So you can just do binary search. So that takes O n time. O log n time. Sorry. Okay, good. So that's the first example of dynamic algorithm that we see. So you see, we have seen divide and conquer. The way to do that is to split problem into subproblem and recurse. It's the same thing here that happened for dynamic programming. Just split the problem into smaller problem and recurse. Many times in divide and conquer, when you recurse here, the subproblem maybe have size something like n/2. Like you reduce the problem size by a lot here, but it can happen that as the last example that we see last time in maximum independent set algorithm, sometimes you just reduce the problem size by 1. That can happen, right? Here also like just from the last like slides, you see like you kind of split problem into subproblem. The problem size get maybe smaller by 1. So it's the same thing here that you just try to reduce problem recursively. But now the point that is different is that for divide and conquer, you have some tree analysis when you analyze running time. But for dynamic programming, what you have is that this will shine. This will like be super good whenever you notice that there are just only small number of possible subproblems that you ever gonna look at. Like this scheduling problem here, we see that the subproblem that we're gonna look at is just n many different. There are just a small number of them. So if this happens, there are a small number of subproblems we're gonna look at. Just save the answers. That's good for you. So that's like basically the way to design dynamic programming algorithm. Step 1, kind of write down recursive formulation. And what you need to notice is that in this formulation, there are just small number of distinct subproblems. If that happens, then it's gonna be good for you. Dynamic programming is gonna be very effective. So bound this thing. And once you see that there are small number of subproblems, now just write down create a table and try to fill in this table bottom up. Yeah. Okay. question about this? Okay. Now let's look at like one more. Oh, shoot. Sorry. More example. The next example is the edit distance problem or like a autocorrect problem. Like for example, someone just type a word like some word, I don't know, and then you need to suggest the correct word. So what you want to do is like a kind of you want to find like a some word that is close enough to this word and it's a real word, right? So now, like to do that, you at least need to know the distance between any two words. So what does it mean? So edit distance is just the total cost of edit operation that you want to transform from a word A to another word B. Okay. And for example, there can be like a three type of edits. One is to insert some character, and each insert you pay like you pay CI. Each deletion you pay CD, and each swap you can pay like a CS. Okay. So basically, what you need to do is just to assign like a low cost. Assign low cost if you believe that an operation is common. Like so if for example like this maybe insert is lower than like the cost of inserting is smaller than the cost of deleting, something like that. Or you just for simplicity you can think of each of these as one, two, doesn't matter. Okay. Let me give you some example. So actually like edit distance here is like another way to look at it is just another problem which I call string alignment. Maybe it's good to see example. Like suppose that you have two words A and B. It just look this is word A and this is word B. Okay. And so now like you basically want to align each character so that they look as similar as possible. So how to align this? It just means that you need to insert like a blank character into string A and B to minimize the cost. And for each of the index here, if some index here from A to B they are the same, then you don't need to pay anything. But if they are not, then you need to pay something. For example, if this thing is blank and this thing is E, it's like you need to insert E here. So you pay CI. You pay CI. The same thing here. And here you need to swap from L to T, so you pay CS. And here you need to delete from R to blank, so you pay CD. Okay. So this is one way to align one way to align B and A. And this would mean that the distance from A to B is at most 3 insertion here, 2 deletion, and 4 swap. Okay. And basically what we want to do is just to find a mean cost alignment. If you find a minimum cost alignment here, then like it gives you like the best way to edit from A to B. So before I go forward, like does the problem make sense? Now we just wanna basically say, we ask like, how do we when should we insert a blank character into A and B so that this alignment have minimum cost. That's our problem. Okay. Question about the problem. Okay, so just want to mention that this problem is extremely useful in bioinformatics. Basically, people need to kind of like they want to know like you have some like they have some genome. Like, let's say you have some DNA sequence, such that this DNA sequence might be like you might have some error in this sequence, and now you want to know like to which genome does this DNA sequence come from. And it's used really a lot. You can look at this software, for example. Okay. Anyway, let's look back to our problem. We want to solve it using dynamic programming, and the first thing you need to ask, like, okay, how do you come up with recursive strategy? Okay. And so the way to look like, so just like before, there is kind of natural way to recurse. That is, let's look at the last pair. The last pair of maybe look at the last pair of last pair of character from A and B. Okay. Well, there are like actually 3 choices one can make. The first choice is that maybe we want that in the last pair, we actually want to delete L from L to blank. Okay, so that is like when in our alignment, maybe we want L here and this is blank. Okay. There are another choice that is maybe we actually want to insert. That is, we put blank in A, and then you put the last character of B, which is E. The next choice is just to swap. Just swap from L to E. That's really just like 3 possible things you can do. There are actually like another case. Suppose that this is L here. Then what should be the thing you should do? Just align them together and recurse on the rest. Because just put this together is always good. You don't pay anything. Right? Okay. So that's now like that's the 3 choices, and for each of the choice, you know like how to like the cost of each choice. If you delete in the last index of your alignment, you just put you need to pay delete, and you just recurse on what? You recurse in like in the first word A, but you delete L. You don't have L here. But here you need to recurse on the whole whole word B. Okay. In this case, you just recurse on the whole word of A, and this one you don't have E. You don't have E. And if you swap, you just kind of delete the last character of both A and B and recurse. Okay. So now that basically just gives you like the recursive formula, right, for edit distance. So let A star and B star be like the version of A and B, such that you delete the last character. Now just from this example, you see that you can just write down it in this way. You either delete the last character of A, or you insert the last character of B, or you like if they are not the same, if the last character are not the same, then like you pay CS. But otherwise, if they are the same anyway, you just pay 0 and recurse in A star and B star. Okay. Does this algorithm make sense? So now I have a question for you. What is the type of subproblem that can ever occur in this recursive formulation? Like whenever we want to think about dynamic programming, we want to count how many subproblems that can there be, right? When you do this recursive algorithm, how many subproblems can there be? Can you tell me?
I think it would be like the length of A and the length of B times together, because you'll have like basically all the combinations of A and B. So like, for example, like AP and the entire polypeptide, like the distance between them. So if you calculate every single possible variations of that, that's all the subproblems.
Good. Yeah, so the answer is they just like the number of subproblems that can there be is just the length of A times the length of B. And why is that? Because when you recurse here, you know that A is always the prefix of the whole word here, and B is always the prefix of the whole word here. How many prefix of this is there? Something like the length of A, the length of original A. This is how many prefix are there? Just the length of original B. So that's the number of subproblems you will look at. So that's a good sign, right? When there are a small number of subproblems. And now you are done with the first step. You get the recursive formulation and you bar the number of subproblems. The next thing, just to fill up the table. Right? So you have the table. Now it's going to be 2-dimensional, not 1, like before. And now you just put like a sum base case. That is, this is just, you put 0 here just to indicate that this is a distance between two empty string. And each point here should mean that this is a distance from this word and this word. Okay. So what you want to compute is just the last guy in the table. Okay, good. So now you see what you have this a table that makes sense. Each of the entry in the table is just the solution of the subproblem that you need to compute, and that's everything that you ever need. Okay. Although you need to compute the last guy here, but what you're gonna do is just kind of fill up this table from bottom up. Now you just write down the algorithm, how to fill up this table. Well, okay. That you're gonna need to fill up the base case. Why does it look like this? So what does this mean? This is the way to match distance. It's just the distance from two empty string. How to edit from the prefix of A to empty string. So that's just to delete everything J time. What is this? It's just the distance from empty string to prefix of B of length K. So that's just like a K insertion. So this is like a base case. And the next thing is just to fill up everything else. How do you fill up everything else? Just use the recursive formula that you have before. So now you see like each of the iteration, everything here just need constant time, right? This is just like a constant number of computation, and there are A times B iteration in the loop. So that's your running time, A times B. Okay, just an example. So you see, like let's say that I put it this like I assign like all this thing like CI, CD, CS to be 1. Then what you fill up in the first is just the base case here. Either to delete everything to empty string or to insert everything from empty string. So this is the base case. And now to fill up each thing in the table, well, you just use the formula here. Okay. Just fill up everything again and again until you get the last guy, and that's your answer. Okay. Question about this algorithm. Is it clear? Good. Okay. I just want to point out one way to view this algorithm that is maybe nice to see. So if you look at this table, actually it looks like a graph, and such that this graph is the directed graph, and each edge have some weight here. Like, for example, the weight here is just CI, because and the weight here, the weight on horizontal edge has weight CD, and the diagonal edge will have weight either 0 or CS, and the condition is just whether the character of that index from two string are the same or not. Right? If they are the same, you put weight 0, and otherwise you put weight CS. Okay, and you can see that what you want to compute is just basically like the shortest path from this node 0, 0 to node mn in this graph. Yeah. So that's actually another way to look at this algorithm. You really just create this table, like this graph, and compute the shortest path. Okay. So I want to mention one thing about the state of the art of this very simple problem. Like you have kind of relatively simple algorithm with A/B running time. Can you improve it a bit, like to like A times B to the 0.99? That's very natural. Like this basic question should be improvable. It turns out that the answer is like surprisingly like no. If you can improve it, it's gonna contradict some conjecture that people believe. So this is like kind of conditional lower bound. If you can improve this, you will improve. Like you will basically solve set faster than what is known. So yeah. So if you want to learn more why, like what does all this means, like you can look at this paper, and actually there is a whole course that try to teach how to argue that some problem cannot be improved further, even by like any polynomial factor. Like it's called like a fine-grained complexity theory. And you can learn more in this class if you are interested. Anyway, so that's edit distance. Question, yeah.
Yeah, so kind of going back to like autocorrect, is what it's doing just computing minimum edit distance for like a bunch of words and then returning the word with the lowest minimum edit distance?
No, it's like here. So here is really the problem. Here is really just you have two words, right? And you just want to compute one number, like the distance between these two words. So now if you want to use this for autocorrect, now you might need, like you have a word that's given to you. Now you have a list of words in your dictionary. You need to compute distance from the given word to everyone, and you might return the best guy.
And the best one is generally going to be the one with the lowest minimum edit distance?
Yeah, right. But what I describe here is just how to compute the distance from one pair of words. More question about edit distance. Okay, good. Okay, let me give you more example. Like we're gonna just see a bunch of example again and again, so that it's thinking like how to design the dynamic algorithm, dynamic programming. Yeah.
For the previous problem, like on your phone's autocorrect, does it do that whole thing like every time or how?
I'm not sure, honestly. I don't know. Yeah. I think that there should be a better way. I'm not sure. Yeah. Okay. Do you wanna have like a? Actually, do you think it's a good idea to have like a short break, like 3 minutes in each class? It's a good idea. Okay. Then like let's take a short break for 3 minutes.
Back to the classics.
I think it's lucky. It's actually kind of crazy. Like autocorrect is that simple.
Yeah.
Because like it seems like pretty logical. Like find like the most common words.
Yeah.
And then match your list of words. And like
No way they run it every single time.
Okay, but really,
It's gotta be like.
let's say we're comparing with 100 words for each word.
Yeah.
Dude, our phone can run at like 0.0 in 1 second.
Yeah.
9 times 100.
Yeah. I was like,
That's no computation. I'm sure it's more complex.
yeah.
But like ultimately, like it's really that simple. That's kind of crazy.
We can't do better. Allegedly.
Allegedly. I feel like if you prove this wrong, though, like the world would end probably.
Huh?
And a hypothesis is wrong, like the world would end.
Yeah.
I think if we prove like people, the world would die.
Yeah.
Straight up.
Stuff like, yeah, this is way too long for DP. It's like DP, each one takes about a while. Like, I think if I try to figure out any distance on
Maybe aliens. They already did it, you know.
yeah.
Right.
Basic algebra.
Maybe the government has broken like RSA.
Have you ever watched? I mean, RSA is pretty
Yeah, like when
It's
he
still
was
assumed to be like factoring is still assumed to be hard.
young, but like now I realize how good he was at like organizing stuff.
Who's how to hack your password?
Have you ever watched Silicon Valley?
Double check my information.
Yeah.
Because I'm pretty sure that's
They
how
have
it
like an
sounds.
AI. And what happens is the AI is actually it develops an algorithm that makes people do.
Really?
Yeah, so then they shut down their computer because
I just start making my discussion slides. I'm like,
It's in the show? Like
yeah, like what happens is so their AI, so it's like a data compression competition, like they're sending messages.
Yeah.
What happens is decrypting messages is vastly easier than them.
yeah.
And so like user data isn't safe over the network. Yeah.
I think Jimmy doesn't want to leave.
Series finale or something.
Yeah.
Oh,
My
really?
bad if I spoiled it for you.
Oh no, shit. Nah, I mean, it's not on Netflix, is it?
No, I'm on HBO Max.
Oh.
Yeah. There's a Jimmy F-bomb counter in the Discord that I told him about. Yeah. Or like every time he like swears in lecture, someone just like plus one Jimmy F-bomb. I don't think if there's like an official count.
That's exactly what I'm doing.
But like every time it happens, someone like talked about making a Jimmy counter. I don't know if that's actually possible.
All the way back up. I was just kind of confused.
Okay. So let's resume.
Something good.
Is it Knapsack
Okay.
called Knapsack?
So now
Like I'm sure.
let's look at our third problem today. Okay. So this is just another like natural problem. Think like you have a bag, a knapsack that can contain at most like W pounds. It can hold at most this much. Like, and think of W as integer. Okay. And now what you have is that you have n things. Okay. Each of the thing Ti has two numbers. That is, it has a weight Wi, and also it has value Vi. Okay. Natural question. You want to pack as much as you can into your knapsack, and you want to maximize the value. That is, you want to find a subset of things. Let's call it S. Like this is just a subset of indices, such that when you sum up the weight of the thing that you collect, this sum is at most the weight of the knapsack that you can have, and you want to maximize the total value. Okay. Very natural question. And now I have a question for you. What should be the natural recursive algorithm for this problem? Let's say that you have n objects. Anyone can tell me the natural recursive formulation?
For each object, you either have the option to pick it or not pick it. So if you pick it, then you subtract that object's weight from the capacity and you add its value. And if you don't pick it, you just go to the previous item and consider those.
Good. Yeah. So that's good. Exactly. So imagine that you have the problem, knapsack problem, where like you have n things, and it's a problem where your knapsack have capacity W. So you have n things, just look at the last thing, Tn. You have two choices. If you want to reject this thing, it's just recurs on everything else. Your capacity is still W. Otherwise, you add it into your collection. You recurse on the same, like the remaining objects, but now it's the same problem except that the capacity is now reduced from W to W minus Wn. Okay? And can you tell me how many subproblems you will ever look at? Can you bar the number of subproblems from this recursive formulation?
N times W.
Yeah.
Yeah, you can have any weight like less than or equal to W, and you only consider like 1 to n items.
Exactly. Very good. Thank you. Yeah, so there are only n times W many subproblems you're going to look at. Because again, like you only look at the prefix of things. There are n many prefix. And W here is just can range from 0 to W. So now that's kind of the first step. you get for recursive formulation with small number of subproblem. Next, again, right? Fill up the table. Okay. You have this table. What you want, like the table is just the table of, let's say this is like a I and this is W. What you want to fill in here is just basically knapsack from this up to TI, and this is W. This is let's say this is W prime. So each entry of the table have like it's just an optimal solution in that you will look at of the subproblem that you might need to look at, and what you need is just the last entry in this table like before. So now once you have this formulation, you create table. It's kind of immediate again. How should it be? Like how should the pseudocode look like? Just try to fill up the table from bottom up, right? And I will not go like into this pseudocode in details now. But the idea is that you have this table, you initialize the table, you fill up some base case of the table, right? Like the edge case of the table. So this is like the table, the entry, like that is like a kind of at the edge of the table. And now for everything else, every other like entry of the table, how to fill up, just use the recursive formula that you have. Either to reject or accept, and you return the max, like use the maximum number, like maximum number of that. And then what you return is just the last entry in your table. So what's running time? What's the running time of this algorithm? Yeah.
Just O of n times W because you have to compute everything.
Good. Yeah. It's O times NW. Yeah, O of NW. Just because there are like NW iteration, in each iteration, it just takes your constant time. Simple enough. Okay. One note I want to tell you is that so this is a simple problem, and like and you can solve it in NW, but you see like it's quite like in our algorithm here, it's actually quite important that all the weight of things is integer. If they are not integer, actually there can be infinitely many possible subproblems, right? And actually, if that is the case, then actually knapsack problem actually become NP hard. So like we get this kind of fast algorithm when the weight are integer. So what we have seen so far until now is that we have seen how to design dynamic programming, such that the table that you fill up is 1D or 2D. And you can see that like for some other problem, there can be like a 3D table that you need, because there might be like 3 parameters that you need to keep track of.
So is there any reason you couldn't work with any irrational decimal? Like if you have to the first decimal place or second or whatever, you can just multiply.
No, okay, good question. So if you are given the weight, which is rational, you can actually just multiply everything so that it has like the weight become integer, and you can work with that. I guess my point is suppose now that let's see. If we want an algorithm such that it doesn't have dependency on W, that's what I mean, then this problem is NP hard. For example, you cannot hope for algorithm that has running time just n to the 10 without W dependency. Your question?
Yeah, so my question was, isn't Knapsack like already NP hard even with the integer thing? Because
So
it's not efficient in W.
So I mean, okay. So what I mean, so when I said that knapsack here is NP hard, I really mean knapsack question when you don't have dependency on W.
Okay.
Yeah, that's hard. Does that answer your question?
Yeah.
Good.
When time is in depth from W. Okay.
So one story, you might wonder like how come this is called dynamic programming? What is dynamic about it? Right. So basically, so first of all, this guy Bellman is the one who invented this concept, dynamic programming. If you learn about reinforcement learning in machine learning, like this Bellman guy is like the key guy who kind of invent this, like dynamic programming is used a lot in reinforcement learning too. But anyway, the reason behind this dynamic programming is that in the 50s, programming just means algorithm actually. So there's nothing about that. Like before, people that have word like a linear programming there is just mean algorithm. Okay. And for the word dynamic, there is no deep reason behind it actually. Like this guy Bellman just try to choose some word such that it sounds positive to everyone, including his boss at the time, because his boss kind of is the guy from military who kind of hate research so much. So like somehow like he need to come up with a word such that even this guy feel good about it and don't reject his proposal. So it's this is the boss. Anyway, the maybe better word for dynamic programming might be like a tabular recursion or memorization. Like because the key thing here is that you identify that there are small enough number of subproblems that you can actually store it in the table, and you just remember out of them. You never recompute again and again on each subproblem. Okay. So let's see. I'm wondering if I should go on or not. Maybe. What do you think? Maybe one more, right? One more small thing. Okay. So I'm just gonna repeat again. This is the key step for dynamic programming. Keep this in mind. Like just come up with a recursive formulation with small number of subproblems. Once you have that, you're kind of done. The rest is just fill up the table. So now let's look at one problem now, such that like it's gonna be less, just a bit less, like less straightforward. How do you come up with the recursive formulation? Okay. The problem is here. You have, let's say, k many matrix. Oh. You have k many matrix. The ith matrix is of this dimension ni times ni plus 1. Okay. So now the goal is basically to compute like the product of all these k matrices. And by the way, let's say that like the cost to compute like a two matrix product, let's say of size m by p. Let's say this is m by p and this is p by n. The cost to multiply this matrix product, at least trivially, is just to spend m p n times, because for each entry you spend p time. Just do it like in the trivial way, in the straightforward way, and there are mn entry that you need to fill in. Right? So let's say that we use the straightforward way to compute matrix product. Now, one thing to note is that matrix multiplication is associative. That is, when you want to multiply A and B and C together, you might like multiply B and C first, and then multiply to A, or you can multiply A and B first and then multiply to C. This is like something that you can choose. The order of multiplication you can choose, and this order matter. Like each different orders give different costs. Let me give you an example. If A is of this size, n by n, B is of size n times 1, C is of the size 1 times n. Okay? So if you multiply A and B first, right, that takes you n squared time. And once you get A and B and multiply it to C, like AB is, how does AB look like? A times B gonna look like, when you multiply it, it's gonna look like this thing. This is AB. And then you multiply by C, that takes another n square operation. So now this look like something like ON square. But if you do it in a different order, you multiply B and C first, right? That's gonna take you n square. But now, once you have B and C, you get some matrix of this size. This is BC. You multiply it to A. Now that takes you n cubed now. So the order really matter, like which one you want to multiply first. Okay. So that's the question we're gonna look at. We wanna see the parenthesis structure. How do you order the multiplication such that it minimizes the running time of your multiplication. Okay. For example, the best way to multiply these three matrices is this parenthesis. Okay. Okay. So, and like what we want is a fast algorithm to compute this parenthesis. All right. Like, so the fast algorithm here, when I said our algorithm is fast, it's just how do you come up with parenthesis structure that is the fastest. We don't count the time to multiply the matrix itself. It's just the time where you come up with the order. Okay. And if you look at this, like this problem is secretly like a tree design problem, because if you have, let's say you have 6 matrix, the way is that like you can decide which one to multiply first. It might be like between A3 and A4, and then you need to check which one to multiply next. Well, you might now just multiply your thing here to to this guy. And so on, like you keep pair up two metrics that you have so far until everything is paired up at the end. Okay. So you see, this is kind of how to decide like a binary tree. Okay. Now, okay. So now, if you view this as like a tree design problem, now it's become clearer actually. How do you come up with a recursive strategy? Why? Because you know, like you have a tree, and the tree must have a root. And what you need to decide is whether like where you want to make a split on the top on the root. Here you make a split at A5 and A6, right? And once you have a split, you just split that. And now it's kind of clear like what to do on the both sides. That's just the same problem. It's just a tree design problem on the left and on the right. Okay. So all you need to do is just first, the recursive algorithm is, okay, you have a sequence of metrics. You just need to decide what is the last multiplication where you want to split. And then just recurse on both sides. Okay. So basically, once you have decided where to split, right, recursively on each side, and then once you have recursed, like once you have compute what is the best way in the recursive in your subproblem that you recurse, then you just take how much you need to multiply like the result of both recursion together, and that's gonna be just the dimension of where you split, like n5 times like n1 and n6. Just basically the dimension of this thing, which is this matrix now, like this product now would look like a n1 times n5, and this product, which is just the trivial one, looks like the matrix of size n5 times n6. So when you multiply these two sides together, you pay this much. Okay. So now, can you tell me? So that's the recursive algorithm. Can you tell me how many subproblems we're gonna look at? Yeah.
N squared in terms of the number of matrices, because each subproblem is just a subarray or sub list of like.
Yeah. So let's say I use the word like in my slide I said that there are k matrices in total. So there will be k square many subproblem we're gonna look at. Why? Because like the subproblem that we're gonna look at looks like an interval, like a sub list of your sequence. It's not just a prefix. Now it's like you can choose where to start and where you end, right? So that if there are k matrices, you have like k square many sublists. Okay. So that's now like once you know this, like you have recursion and the total number of subproblem is small. The same thing. Like Now just fill up table, and you're kind of done. So just write down like create the table. It's like a memo, and fill in some best case. And you can check that this best case makes sense because, okay, first of all, this table, the meaning of this table is that I want to set that on the entry ij, right? This should store the best solution when I want to multiply matrix from like the matrix such that the first index is ni and the last index is like the last parameter of the dimension parameter of the last guy is nj. Okay. So just maybe I should start from the beginning. Let's say that there are like I want to multiply matrix from ni up to a1 up to ak, right? Here there's gonna be actually like a k plus 1 numbers that describe this problem, and then like this is like the memo of I and j is just when you recurse and they start from ni and end at nj. Okay. And then like this is just the best case, and in the general case, how do you like fill in the table? Well, you just say that okay, in the table at entry ij, what you need to do is just to choose where you want to split, right? So this parameter h is just like it's just the index that you want to split. You want to split at index h. If you split at index h, the cost that you're gonna pay is this much. This is just the time you need to multiply at the end, and then you recurse on the left side and recurse on the right side. Okay, and you just fill up the table. This is just so I won't go into details, like but like it makes sense in high level, right? Like it's just fill up the table. Except that there is one thing that is wrong about this. If I just write down the for loop in the natural way, like this, there's something which is wrong. Let me tell you why. So, okay. Basically, we need to iterate. Like, we need to fill up the table in the right direction now. So, if this is index I and this is index j, these are the best case that I fill in. Like, and everything here is not even like everything here is not even something that I need to look at, because when I is more than j, I never look at this case. This is the best case, and the way we want to fill up this table is that we need to like fill in from like kind of going in this direction, right? So like once you have filled in this best case, you need kind of to go through the table in this way, kind of so that but in the for loop that I drew, that I have here, is just kind of just go in this direction, and that's not good, right? Because let's say you kind of go in this direction. If you want to compute this, it kind of relied on the table here, and that like you didn't compute it before, so it just doesn't work. So all you need to do is just to change the for loop here so that it go in the right direction, and That's it.
If you formulate the loops in terms of like start index and length, and so start index and end index, would that make it easier to go?
Yeah, the start index and length.
Okay.
That's the way to do. Yeah. So that is like a non-decreasing order in j minus I, which is the length. So now, if you analyze this algorithm, it's gonna take actually n cube time, because there are like a kind of n square thing that you need to fill up, and each entry you spend n time. The state of the art here is like a n log n, but we won't look into that. Okay, so next class, still a bunch of example of dynamic programming. So see you next time.
Last